Hey guys, welcome to the first video for AP Chem. In the first series of videos that I'm going to ask that you watch, it's going to review stuff from Chem 1 that I'm going to expect that you remember. And these are things that I am not going to teach you in class, but they will be assessed on various daily quizzes and tests and things like that. So it's important that you go through these notes and take notes, go through extra practice. If you need extra practice, I do have it. But just keep in mind that these are not things that I'm going to take class time to formally teach you. I, of course, will help you and review with you in any way that I can, but I'm not going to be actually taking the time to teach these things to you because I'm going to expect that you remember them from Chem 1. All right, so the first section that we're going to look at is the first part of Chapter 1, which deals with just the definition of chemistry and scientific method and things like that. So I'm going to go through this very briefly because it is a lot of just definitions and conceptual things. So chemistry by definition is the study of matter and its interactions. Some of the interactions that we are going to be looking at are things like reactivity, boiling point, melting point, viscosity, density, color, things like that, and we're going to be looking at why compounds have these particular properties and what about them causes the different reactivity, boiling point, melting point, things like that. So IMFs and bonding angles and all that good stuff. Okay, so Chapter 1 in your book first looks at scientific method, and science by definition is the pursuit of knowledge about the natural world and the universe. And the scientific method, I'm sure that you've learned throughout the years to have multiple different parts. I'm going to condense it into only 3 components. And so the first part of the scientific method is to observe, or I'm going to also add that you're going to be collecting data during this section. The second part is going to be to form a hypothesis, and I'm not always going to ask you to formally write out your hypothesis, but I would encourage you to, as you're going through labs collecting data, to think about hypotheses, think about what's going to happen, what should happen, that sort of thing. Again, I very rarely will ask you to formally write them down, but it's a good thing to be thinking about as you're going through different labs and experiments. Once you've collected that data, formed those hypotheses, you then can do the experiment. Once you've done the experiment, you'll be able to form theories and models and laws and things like that. Laws and theories are different. I would say that models and theories go together because theories are, after all, just models, and then laws are the second thing. Next, it's important to know the difference between a theory and a law. I think that this is one of the most commonly missed concepts for students, is that, and people in general who think that laws and theories, one is sort of not true while the other one's true and that sort of thing. There's a little bit of a difference between the two, and I think it's important for you to know the difference. So a theory is a model that's based on a set of hypotheses that agree with observations. So for example, we study atomic theory in here. So the model of what the atom looks like. It is based off of experimental data, and as scientists have found more experimental data, they've changed what the atom looks like. So that is an example of a theory. And the next, a law in comparison. Law is just an observed behavior. It's a statement, it's a description, what we see, this is what's happening. Gravity, for example. Gravity is a law. It's observed. When things go up, they come down. It's pretty factual, just a statement, succinct, this is what happens, it's a law. So a way that I like to describe the difference between a theory and a law is that a law is just a statement of what happens, and a theory tries to explain why. So a law is a statement, so it summarizes what happens. So it summarizes what happens, it summarizes what we see, and a theory tries to explain why, or a model. And of course, there are problems with scientific method with these observations, and you have to look at things like biases, selective data, human factor, that sort of thing, which are all going to be in the next slide when we talk about error. So throughout this year, you're going to be writing some lab reports. And in the analysis section of your lab reports, you're going to need to be talking about error. So what specific things happened in your lab that resulted in errors being made or resulted in your labs not having maybe the results that you want. There's two main types of errors, and I'm going to ask that you write about both of them in your lab report and be specific about them. So the first one is called random error, and the second one is called systematic error. Random error is just that. It has the same probability of being too high as it is to be too low. It's random. Things like rounding, those are all examples of random error. Systematic error is something that is always too high or it's always too low. An example of systematic error is poor technique. If you are unsure how to use a piece of lab equipment, you're going to make that same mistake over and over again because you don't know how to use the lab equipment. So that would be a systematic error. I'm going to encourage that you on your own time watch this video. It does go into detail about the difference between systematic and random error. One thing here, I kind of alluded to it, but because random error has an equal probability of being high or too low, this is why we do multiple trials. And so when you do a bunch of trials and you average them all together, you're going to have an increase in accuracy. And so you will notice in many of our labs, we'll do multiple trials and then you'll average all your numbers together. And the reason for that is so that we can eliminate that random error or at least reduce it. Another thing that we need to think about when it comes to error is looking at sig figs and looking at measurements and dealing with the uncertainty that comes with the different lab equipment that you're using. So the level of uncertainty that you have deals with whatever the lab equipment that you're using. And another name for that is sig figs. And we'll talk about counting and rounding sig figs in the next video. But when you're looking at a piece of lab equipment, the general rule, as it says here, is that you need to look at the numbers in between your graduations. And so one thing I like to say is just you're going to measure one number past what's known. And so if we look at this graduated cylinder here, this line is 2.0 milliliters, so I know it's above that, so I know it's at least 2 milliliters. And if I count to 1, 2, 3, 4, 5, so this is 2.5, and that means each one of these graduations is a tenth. And so this one right here is 2.1 milliliters. So I know that my meniscus here is at least 2. It's not quite 2.1, and so I'm going to estimate that the amount of liquid in this graduated cylinder is 2.06 milliliters. So I know it's at least 2.0, and I'm going to go one number past, and so I would measure it, I would record it as 2.06 milliliters. Now this number 6 can be different. Maybe you look at it and think that it's 2.07, 2.08. That's fine, as long as you know to go one number past what the graduations tell you. And all the lab equipment that we have in our lab have all different graduations. So it's important that you look at the graduations on the piece of equipment that you're using and always measure one number past what it's showing you. Okay, and then the last thing that I'm going to discuss in this video is accuracy and precision, very, very briefly. So accuracy compares your measured values with the true value, so you're looking at how close you are to the intended target, whereas precision deals with reproducibility, so how close were your trials to one another. And this is the common analogy with the dartboard. So if you look at this bottom picture, this one is both accurate and precise. All of the darts are close together and they're right on target. Whereas this one in the opposite corner, they are not near the target, so they're not accurate, and they're all kind of all over the place. So again, they are not precise. If we look at this particular trial, so apparently this lab was collecting the density of lead. So they did multiple trials, as you should. And then once they did all your trials, they averaged and got the average density here. So if you ask yourselves, if we know that the accepted value for the density of lead is 11.2 grams per milliliter, is this data accurate? Well, it's kind of hard to see based on the individual trials, but if you average them together, you'll notice that the average is 11.6. So I would say that this data is pretty accurate because your average is right on the nose with the accepted value. Is this data precise? I'm going to lean towards no. It's a little bit subjective to figure out whether something is precise, but you know, you have 0.1 and 0.0 are pretty close, but then this one's 0.6. They're kind of all over the place. So I'm going to say that it's not precise. Obviously, the best outcome for a lab is to be both accurate and precise. We're not going to be spending a whole lot of time looking at the differences and things like that. I would say you're probably going to be dealing with accuracy more than anything in this class, looking at your percent error and things like that. That all deals with accuracy. So I would say that we'll focus more on accuracy, but it's important to look at precision and know whether a lab that you're doing is precise or not. The next video that I'm going to record and that I'm going to have you watch is about sig figs.